Comparators. So we looked at exclusive ORs and exclusive NORs, and that's basically what a comparator is. The comparator that we were looking at was a magnitude comparator called the 7485. And this is the actual makeup of the 7485. So this is one of our exclusive gates right here. We're going to go back and look at them. But what's nice about it's what we call a 4-bit comparator, right? You understand that? So what it's doing is comparing 4 bits to 4 bits. And then it's telling us if what. So there's calling one of the bits, they're calling it A. So this is the pinout. This is the symbol we normally use. So normally over here, when we draw schematics, we put inputs on the left and outputs on the right. So normally this will be the schematic symbol you'll see, but this is the actual pinout. If I was going to wire this thing up. So what we got one nibble right here, we call A. We got another nibble right here, we call B. And this comparator is comparing the A bits to the B bits. And it's telling us what? It's telling us what? So I got 3 outputs. What are those 3 outputs telling me? Well, if this one's true and the other 2 false, it's telling me that B is greater than A. If this one's true and the other 2 false, it's telling me that A and B are what? Equal. If this one's true, then what does that mean? It means A is greater than B. So what this comparator does, we don't really care how it does it, but it's comparing 2 nibbles, right? You understand? One of them they're calling A and one of them they're calling B, and it lets us know if they're equal. If they're not equal, it's telling us what? Which one is greater. And then we got this expansion right here. Notice this says input A is less than B. This says input A is equal to B. And this says input A is greater than B. So what we can do with this guy is we can string them together. So I can take the output of one and do what? Feed it into an input of another. So what we're doing here is we're comparing 2 bytes to see if they're what? Equal. So here it would say byte B is greater than byte A. This says byte A and byte B are what? Equal. This says byte A is greater than B. So what we can do with the 7485 is basically we can compare a lot of bits. I could take the output of this one and feed it into another one, right? You understand? And then we'd be dealing with 3 nibbles. I could take the output of that and feed it in another one, and then we'd be dealing with a 16-bit word. So this is a magnitude comparator. I think this is the guy I was using. We had a problem with a post mill machine out at Leach's Machinery. And it was messed up. And everything was done with transistors. I mean, the whole thing. So there'd be hundreds of transistors on this circuit board. And one of the transistors that did the comparing. So what the machinist would do, he would go on the panel and he'd enter where he had thumb wheels, and he would enter where he wanted his mill to go to in reference to 0, and he'd press a button. And that's all it was doing, was comparing the counters, the counts coming off the actual machine itself to the counts that he put in. And when they matched, the thing would stop. But what the problem was, it never matched because one of the magnitude comparators had gone out. And this is exactly what I used. I can't remember if I had to use 1 or I had to use 2. I think it was just one of the nibbles were messed up on it. But So I pulled out the bad transistors and put an integrated circuit on there. You didn't see it. The machine might still be working out there. I don't know. Then we have these decoders. So that's a magnitude comparator. Everybody okay? 7485, really neat IC. And then we have decoders. What does decoders do? What does a decoder do? Nobody in the class knows what a decoder is. Get your textbook out and look them up. When we go back to this guy, we know this is nothing but AND gates, OR gates, right? You understand. That's what we mean by combinational logic. So what does the current combinational logic mean? It means when we use the 5 basic gates to create more complex circuits, right? You understand. So I could go back to the transistor arrangement for this guy right there, and that guy uses 1, 2, 3, 4 transistors. OR gates use more. Plus all the resistors and all that other kind of garbage. But it does a NAND function. So what we do is we take that transistor circuit and represent it with a what? With a symbol. So as soon as I represent it with a symbol, I don't really need to know what's inside the gate. All I need to know is what the gate does. Right? So this gate right here says all highs to get a low. Then we get into combinational logic circuits, which is made of all these gates. So this guy's got, that would be 5 transistors there. That would be more transistors right there. That would be 6. That would be 6. This would be 7. So that would be a lot of transistors, and I could draw it out as transistors, but I don't need to do that, right? You understand? Then we take those and put them inside and create combinational logic, right? You understand? Which uses a lot of NAND gates, a lot of NOR gates, but I don't even really need to know that. I need to know what I need to put on the input and what to expect on the output. So what I need to do is I need to understand it from this point of view. Right? You understand? And if it don't do what it's supposed to do, I can't go in there and do what? Change a transistor in that NAND gate right there. I changed the whole gate. I changed the whole logic circuit, right? You understand that? So this is that nice to know stuff. We need to see the inside of the transistors just to understand about syncing and sourcing and why did it clip off this and why did it do that. But once we learn the basics of the way these things work, we troubleshoot them from what? Of course, that's a negative NAND, which would be actually a NOR gate, right? So these are comparators. Now we're going to get into decoders. So what does a decoder do?
Self-explanatory.
Huh?
Really self-explanatory.
Well, explain it to if it's self-explanatory.
Well, it decodes.
Yeah, but what does it decode? It does something specific.
Okay.
Huh? But we have encoders and we have decoders. And so what you're telling me right there would mean exactly the same thing. Right? You understand? That would be like me saying, what's the difference between a Ford and a Chevrolet? If there was no difference at all, everybody would be driving the same thing, right? You understand? So they have a function in life. These guys have a function in life. So we can't say encoders. So I could say encoders and decoders. I could say, a BCD to 7 segment decoder, and you're not really telling me anything. But what a decoder does is take a binary number and converts it over into something else, into another numbering system of code. So we have what we call a binary to BCD. So that means we're going to go from binary, right? You understand, over to some representation of a decimal number. So a 74138 is what we call an octal decoder. So it's going to take 3 bits of binary and going to convert it over to a representation of the octal number system. We're going to have a binary to hexadecimal decoder. It's going to take binary and give us an hexadecimal representation, 0 through F, right? You understand that? And then we got what we call a BCD to 7 segment decoder. So what BCD, it's going to take it and convert it over to a code to run one of these things right here. This is what we call a 7 segment display. Y'all see it? So a decoder converts a binary number or code to another what? Numbering system of code. So we got a binary to octal, or it's also called a 3 to 8 line decoder. We have a BCD to decimal, which is we'll see in the data sheets, they call it a 4 to 10 line decoder. And then we got a binary to hexadecimal decoder, which is a 4 to 16. But they all work on the basic same principles of just taking a bunch of, let me see, wrong way, Rich. Just doing like this. So I just add more NAND gates or whatever. Depends on whether it's got a low active output or a high active output. The 7442, the 74138, and the 74154 has what we call a low active output. So it means I come up here and I put a binary number on the input, only one of these outputs are going to go low, depending on what I put on here. Y'all understand? So let's just look at one of them. So what 4-bit number do y'all want to convert over? 5. Okay, so we come over here and I'll put a 5 on the input. 1, 0, 1. So if this thing's working, that output right there should go low. You understand that? Okay, so we bring this 5 and let's do red and like blue or something. So here comes this one. So that's going to come over here and make this whole line right here red, right? You understand? That's going to come over here and make this whole line right here red because it's inverted. That's going to come over here. This is going to come in and make this whole line right here red. So right now we don't have all those to get a low, right? I need to bring them on over. So that would be, this one would be red, this one would be red, this one would be red. This one would be red. None of those would be red, right? This one would be red. Did I miss any? This one would be red. Or that one right there would be high. This one right here would be high. This right here would be high. And this one right here would be high. Oh, this one right here would be high. Thank you. Miss any more? And then we'll come over here and we'll use blue for the low. So this right here would be blue. This whole line right here would be blue. So right off the bat, that kicks this guy off, right? This guy right here would be blue. That kicked that guy out because we can't get all highs to get low. Oops, missed one. Oops, I'm right. We're okay. This right here would be blue. Wait a minute. This right here would be blue. So that would be blue. So I'd kick that guy out, right? This right here would be blue. Yeah, I did miss one. This guy here out. Right here, line right here would be blue. Kick this guy out. This guy right here has one blue. Kick it out. This guy right here has one blue. Kick it out. Which one has all highs? 5. And they're all basically the same. Whether it's a 4 to 10 or a 4 to 16, it's just they just add another inverter in, more ands and more ands or names. So what would happen, this one would be high, this one would be high, this would be high, this would be high, this would be high, this one right here would be what? Low, and that would be high. So we could go over all the 8 combinations I could put on the input, and it would take that binary number on the input, and the output would go low, indicating what number I put on there. That makes sense? Makes sense? So this would be what we call a 3 to 8 decoder. It's also called a binary to octal decoder. 74138, and then the different versions of it, right? Or family. So we have a 74138, we have a 74L138, we have a 74H138, we have a 74F138, we have a 74LS138, we have a 74 ALS138. So what's the center letters telling us? So I come up here and I say 74138. And then I might have a 74LS138. So what's the difference? It's the speed and what? So speed's nice to know, but another thing, I have to build a power supply. I have to come up with a power supply that has the ability to run all the integrated circuits on this board there. So that means I need to know the power required by every guy on that circuit board before I can build a power supply. If I build a power supply that's too big, then I'm wasting too much money. If I'm building a power supply that's too low, then nothing's guaranteed. So what these center letters telling us is telling us two things. It's telling us the speed of operation, and it's telling us the power required to operate those guys. So L means low power, S means Schottky, which means these guys are extreme power. So a 74H138, that's going to be a high-speed chip, but as soon as I say speed, we're talking about, right, you understand. It's just like when you get out there in your car, you drive at 30 miles an hour all the time, you get really good gas mileage. You get out there and you drive 100 miles an hour all the time, you get really poor gas mileage, right? Because what you've done is you've increased the what? The speed. So the same thing's true in digital. The faster these things run, the more power they consume, which means my power supply has got to provide more power, right? Does that make sense? So those center letters are telling us the speed and power characteristics. So that means once you looked up one LS chip, you pretty much well got all of them, because they're within that family, right? You understand? So you would know basically the fan out. What's the fan out, by the way? So nobody in here knows what the fan out is? Of a gate is? So I highly recommend, guys, that y'all take no online classes. Because why? Undoubtedly, you either didn't listen to the lectures, right? Or you didn't take quizzes. So what is fan out? We don't see it in data sheets. So fan out is the number of inputs this gate right there could drive of the like family. So standard TTL, this guy has a fan out of about 10 gates, 10 input. So it means a 74-138 could, and that's rule of thumb. You'd have to actually look it up. But rule of thumb means that guy right there could drive the inputs of 10 gates. I'm sorry, 10 inputs. So if I came over here and did this, that means this guy right here has 3 inputs. Every one of those inputs pulls a certain amount of current. About 400 microamps for a high and about 1.6 milliamps for a low. This output of this gate here can output about 400 milliamps for a high. It can output about 16 milliamps for a low. I'm sorry, yeah, for a low. So if this guy right here takes 1.6 milliamps to create a low, This guy provides 16 milliamps. That means this guy could drive 16 inputs. I'm sorry, 10 inputs. If this guy requires 4 milliamps, I'm sorry, this is 400 microamps. Is that right? I need to go look that up. And if this guy required 4 microamps, then it could drive 10 loads, right? You understand that? So what is the fan out? So what's the fan out of an IC, of a gate? Huh? Of the like family. So an LS requires less current than a standard series. So a 74138 could drive more than 10 LS things. Right? You understand? So it's of a like family. So when we say fan out, it would be like 74 LS something driving 74 LS gates. Does that make sense? Now, why don't they put fan out in the data sheets? So you'll read it in books. Books will have that definition in there and they'll talk about it. But when you get into the data sheet, you won't find fan out. Huh? Well, sort of, it's a teaching tool. It's not really understood, but you can calculate it, right? You understand that? The problem we have, guys, is that we got so many different families out there. So I've got LS and I've got all these different families, and we use them depending on what situation they're in. So if I say a 74138 has a fan out of 10, that means if it was driving standard symbol gates, but what if it was driving LS gates? Well, you say, well, it has a fan out of 10, but it's driving LS gates. Well, that means nothing anymore because LS requires less inputs. So what we do, and we'll just grab one. So here's a 7404. You know, don't like that one, does it? So it is 400 microamps. So here it says so right here, this is what I've used. Output low, current output low. This says it can drive what? A maximum of what? Right here. Can y'all see this? 16 milliamps. Okay. When I look at my input current, this guy right here says what? My input current, my input would draw a maximum of what? 1 milliamp. So that means this guy might be able to run 16 gates, but it all depends on what? The input currents. So this is what we would do to figure out how many guys these would drive, is I would come up here and look at what? The maximum output current. And then I would go to the gates I'm using and I would look at the maximum input current to actually get the true fan out. So 10 is just a rule of thumb, right? You understand? Does that make sense? So if I had this guy right here driving these guys right here, then I would have a true fan out of 16, because this guy right here can actually output what? 16 milliamps, but only requires 1 milliamp for a load. So this is why they don't put fan out, because why? Because the output currents, so what we need to know is how much output current these guys can drive, and then we would need to know the input currents of the gates, the required input currents on the gate is trying to drive. Does that make sense? So this is why they don't put fan out in data sheets, because it varies with each gate, right? So that would be like when you get you try to figure your gas mileage. What does your gas mileage vary with? You can say, well, I'm getting around, 23 miles a gallon, but you don't get 23 miles for every gallon that you burn, right? Does that make sense? So what we're saying is that if I wanted to know exactly how much I was burning for speed, then we would have to get more information, right? So fan out of 10 is just a what? Yeah, it's just a rule of thumb. But what I really need to do is I really need to figure out, so if I was going to design a power supply, then I would come up here and this is what I would use. I would figure out, okay, what current does this gate require? Right? You understand, to run this thing. So fan out is how many gates, how many inputs, and this is why when we come up here and we do this, so this would be a NAND gate, say a 2-input NAND gate. Well, let's use a 3-input NAND gate. Now, what logic function does that guy perform right there? Performs an inverter. Good. How many inputs with this? Let's say I come over here and just for the heck of it. How many inputs is that guy right there trying to drive? 3. Each one of these would require 1.6 milliamps, 1.6 milliamps, 1.6 milliamps, rule of thumb. Okay, y'all understand that? What would that circuit do? So these right here are always high. So this serves as an inverter. What advantage does this one have? Yeah, so my gate's only driving one load. So you'll see this done a lot is which one is most convenient, which one are you pushing your power supply, right? You understand? So you'll see pull-up resistors used a lot. What's a pull-up resistor? So this is a resistor that we use to guarantee a high. So what advantage does that circuit have over this circuit? So there I'm connecting it directly to 5. This one I'm connected to 5 volts to a pull-up resistor. And according to that, they do the same thing. This guy right here is dangerous to use because integrated circuits go bad 3 different ways. And one of the ways is these inputs can do what? They can short. We had a disk drive that kept the power supply kept kicking out on it. And we call it a crowbar circuit. Most well-designed power supplies will shut themselves down if it senses overcurrent. And what that does, it prevents the power supply from burning up stuff. So we had a disk drive back when disk drives used to be used, kept crowbarring the power supply. The power supply kept cutting off. And what happened is an input to a logic gate shorted like that. This guy had about 100 integrated circuits on there. And why? Because the engineer didn't put a what? They put a pull-up resistor on when he pulled up the inputs gates that were unused. What we doing back there? You already know all this stuff? You play it on the internet or something? Answer an email? Or chatting with somebody? So this is the things you would have to consider if you were designing them, right? And then, but what happens is you run into poorly designed stuff. I know I told you about the scale down in Columbiana, right? So we have a 3 to 8. This is a 74138 octal decoder, also called a 3 to 8 line decoder. So we got 74138. This is used all over the place. This is standard, by the way. All we have to do to change it is just, now if you're looking for the pin out, you're not worried about because the pin out of the 74138 is exactly the same as the pin out for a 74 ALS38. The only time you're concerned with those center letters, if you're trying to figure out how many things this guy can drive, right, you understand, or speed or that other kind of stuff. So 74138, this is a 1 to 8, or also called an octal decoder. We have a 7442, it's also 1 to 10, which is called a BCD decoder, or it might be called a 4-line to 10 line. A 74154, this is a 1 of 16, and a 7447, this is a BCD to 7 segment decoder. So this is the 74. First of all, this is something new. We already know about enable and disable, right? So what do we mean by enable and disable? Huh? Well, but what do we know? Well, enable means we allow the circuit to work. Disable means we don't allow the circuit to work. Well, we're going to pick up another one called what? Don't care. I just don't care. So when we don't care, it means we don't care if it's a 1 or we don't care if it's a 0. So this is a 74138. This is the pin out. This is the schematic. The 74138 is a 3 to 8 decoder. So I'd put a binary number in on here, 0 through 7, and one of these outputs right here would go low. Now this is another thing that gets kind of confusing, is that we have two things associated with a pin. We have a pin number, and then we got the name of the signal that is developed by that pin. Don't understand?
Right here.
Okay. So notice over here, I know this is the common logic gate. This is E. Could be E. I've seen it called S for select. I've seen it called CS for chip select. So these E's it depends on where you're at in your data sheets. So it says to enable this thing, what does it say I need? It says pin 6 needs to be what? High. Pin 4 and 5 needs to be what? Low. Once we've got that situation, then this guy will decode. If any one of these are in the wrong state, then the outputs are going to do something, depending on what the logic says. So when we look at the truth table or the function table, it says here, it says E is high, but it's supposed to be what? Low. It says E2 is high, but it's low. E2 is So as soon as this guy right here goes high, what are these? Don't care. You understand that? So what happens is I'm over here, and this guy right here is supposed to be low and it's high. Well, as soon as that one's high, there's no way in the world this is going to enable this guy. So those other three enables don't mean anything. So it says this is don't care, this is don't care, this is don't care, this is don't care, because all the outputs are going to do what? All the outputs go high. Now they do the same thing on the next one. It says, okay, this guy's high. Well, it's supposed to be what? Can y'all see it? So this has got a bar above it. This has got a bar above it, and this right here don't. So this says I require a what? A low. So since it's high, this guy don't care, 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 and all the outputs do what? All the outputs go high. It says, okay, I come over here. This one goes low, and it's supposed to be what? It's supposed to be high. So this one don't care, this one don't care, this one don't care, this one don't care, and all the outputs go what? High. Then it says, okay, this is low and it's supposed to be low. This is low and it's supposed to be low. This is supposed to be low. And I put a low on the A, B, C, D inputs. Now, unfortunately, normally on these things, they do it backwards. But A0, A1, A2, this is the least significant bit. This is the most significant bit. And I put in this right over here. If I converted that to decimal, what would I come up and get? If I converted that right there, that binary number to decimal, what would I get? 0. Well, look, which output went low? 0. Now we can do any of them. So let's say we do our 5 like we did before. Only when it's enabled, right? You understand? So a 5 would be a 1, 0, 1. But before it works, I have to do what? I have to make this guy here low, this guy over here low, this guy right here. Then I have a high, a low, a high. That's a 5. Which output went low? Output 5. So this is a decoder. So what it's doing is taking 3 bits of binary and giving us an octal representation of that. So only one output goes low, but the output that goes low will tell us what's input, what 3-bit number we have out there, right? You understand? But only if it's what? Only if it's enabled. If it's disabled, then your A1, your A0, your A1, and your A2 input mean nothing. All the outputs do what? All the outputs go high. Do you understand that? Yes or no? That's right. Are we okay? Then we have a 7442. This is a 1 of 10. So this guy here does not have any enables or disables. Sorta. It does it on itself. So we got 4 inputs, we got 10 outputs, 0, and this guy really gets people confused. Now notice what they normally do. They put the name of the signal inside the rectangle, and they put the pin number on the outside. And people get this confused. Because over here we got the 0 input, but it's connected to get the 0 output, we need to use what pin? Pin 1. This always gets people confused. They get the 2 confused. We got inputs called A0, A1, A2, A3. A0, A1, A2, A3. So I can put 16 combinations on this, but we've only got 10 outputs, 0 through 9. So here's the truth table. So all lows, which output went low. So that would be a 0. The 0 output went low. Here this would be a 1. The 1 output went low. Here would be a 2. The 2 output went low. Here would be a here would be a 3. The 3 output went low. Here would be a 4. The 4 output went low. And you can see it does all the way until we get to 9. Now the problem is we don't have a 9 output, right? I'm sorry. So 9, I missed one, guys. I needed to come down one more. So here's 9. If I put a number above 9, the thing's not going to blow up. It's just that it can't decode anything above a 9, and all the outputs will do what? They'll go high. So this is a BCD to decimal. It could be called a 4 to 10 decoder. Are we okay? $74,154, 1 to 16. This is in a 24-pin pack. So, for LS1. So this package right here, I've seen them go up to 18 pins. And that was kind of bent up. So this is the pack we've been using. It's kind of girded up, guys. But this is a standard pack. And we talk about the width and the spacing between the pins. This package, this spacing and this length, the biggest one I know of is 18 pins, which would be 9 on each side, right? You understand? Once we get integrated or get more pins, then the next package size they go up is to this guy right here. So this is a 74,154. And this took us up through a lot of different processors. A lot of the first microprocessors that came out used this width and the pin spacing. The pin spacing is exactly the same as this guy. What's different is the width, right, and the length. Everybody okay? So this is a 74,154. 74,154 has 16 output pins, 4 input pins, 16 output pins, and it's got 2 low active enables. So to make this guy here work, we got to bring enable 1 and 0 and 1. These both have to be what? Low. And my guess, it's got a low active output, so whatever binary number we put on the input, that output should go low depending on whether the chip's enabled.
Does it have a dash over top of it to show that it's supposed to be low? Or how do we know it's supposed to be low?
We got 2 ways that we can tell if it's supposed to be low. That's a perfectly good question. We can use the overstrike, or we can use the bubble. So if you see a bubble, it means it's low active. If you see the overstrike, it means it's not bubble. Especially in data, and that's a really good problem. See over here, I can put bubbles. In my truth table, I can't put bubbles. So what do they use in the truth table? They use the overstrike, right? Wait, Brian. Wake up, man. Don't fall asleep. Stand up. I found out humans can't fall asleep standing up. Cows can, but humans can't. So when we get to the truth table, Notice over here they're using bubbles. Over here they're using overscore. So here, if this is a low and this is high, then what's the other bits? They're don't cares, right? You'll see that. And if this is high, this is low, they're don't cares. This is high, this is high. If they both go low, then whatever we put on the input, so if I wrote down that binary number, converted it to decimal, that would be a what? That would be a what? That would be a 0. Well, we notice which output went low. 0. This would be a 1, this would be a 2, this would be a 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay? So 74 154s. Now encoding is the opposite of decoding. So here we take a code and we're going to generate a binary number from a code, right? Or a binary code. That makes sense? Let's see, 74 147. So here we're going to input a decimal number from 0 to 9, and then this should generate a binary number that represents that. So here we have and this is a low active input, guys. So we would think a 9 would look like that. But if it's low active, then a 9 is going to look like that. So a 0 is true, right? So this would be a 9. And which output went low? Which output went low? I'm sorry. This is the inputs, Rich. So here, input 9 went low, and it decoded inverted 9. Here, input 8 went low, and it decoded inverted 8, right? You'll see what I'm talking about? Yes or no? Huh? How come you say? Yeah, this is a low active output. So that means it's true when it's low, right? You understand? So what we're saying is we see a 9 like this, right? But the output is what? Inverted. So this is going to output this code right here that represents a what? A 9. That makes sense? Yeah, this is an encoder. So an encoder takes another numbering system or code and is going to convert it to a binary. Understand? Now, of course, if I needed this, then I would have to run this through an inverter to get a 9. Because this has a low active output. Yeah, so here's a 9, but it's a low active input. So here's a 9. So input 9 is true. Okay. And this output is this, which is equal to a what? A 9. This right here, so let's just go down here. So this right here would be a what? A 4. So notice this guy right here went low. So if I went in there and wrote that down, and then I inverted it, that would be a 4. And that's just the way this guy works. This is just something you'll have to learn. Now, this is also called a priority encoder, which means the highest one. If you ever have two inputs that go low at the same time, so if this guy right here goes low, and this right here is low, it's still going to decode a 7. So we use this guy right here to set priorities too. 74,148. And we can combine them. So we can use this as a BCD binary encoder. We're not going to go through this. What I want to get to next. 7-segment. Everybody understand what a 7-segment display? So we know what a diode is. What is a diode? What does a diode do for us? In one direction. And of course, electron will flow that way. Well, what happens what's happened is we're pushing things towards the center. And we're not, you'll learn, if you take solid state, you'll learn how these things work. But when these things generate photons. And what's photons? These are what we see, right? You understand? The problem with regular diodes is that it takes very little energy to get these things to work. The photons that would produce would be a wavelength that you wouldn't be able to use anyway. So normally these things are put in dark plastic or something like that. What they found out, so these are made out of silicon or germanium, is they found out, I think it's gallium. I don't know if I'm spelling this right. They found out that gallium creates, a semiconductor creates a lot of photons. And then they can come in and put impurities in there, and they can cause these things to generate different colors. So that means they came out in, I think the first ones were, they were doing okay with yellow. They were doing okay with green. They was having a real hard time with red, trying to get an LED to glow red. And they thought blue was basically impossible. So eventually they came up with red LEDs, which was really neat. So now we had yellow, we had green, and we had red. Then this guy came up and finally developed a blue LED. One, in fact, it was so hard to do when they finally figured out how to do it, he actually won the Nobel Prize for Physics because he made a blue LED. So now we had the prime colors. We had the major prime colors. We had red, we had green, and we had blue. Which means now we could develop what color? Any color. Main thing would be white. So now we can make white. So up until then, we didn't have white LEDs. They were getting close to blue, right? You understand that, but they finally got blue. So what these things do is they only let current flow in one direction, so you have to bias these things correctly. If you don't, they won't glow at all. But if you bias them, then they'll glow them. They'll actually produce light. And they actually produce these colors. What we normally do is we'll encase these things in the color that they produce to make them more vibrant. So normally a red LED, light emitting diode, will be in a transparent red lens, right? You understand? So now we make light. So we come up here and they say, well, what can we do to take advantage of these things? And the first thing they said, well, what I need to do is be able to display numbers, right? You understand? So they came up with what we call the 7-segment LED. So they arranged LEDs in like this. And mine's don't look good. But now what can we do? Well, I can turn this guy on. I can turn this guy on. I can turn this guy on, turn this guy on, turn this guy on. And what would you see? You'd see the number 3. So now we can display numbers. And these guys are still used a lot out there, 7-segment LED. So this is a big one. This is using multiple LEDs on it to do this. So this is this is a real use set. These are LEDs. They're red, and they got a red lens on them. And then we can diffuse it to make it spread out, or we can focus it toward the end. These are all focused toward the end. And you can't actually see, some of them you actually see where it makes the diode inside stuff. So we can come up here on these LEDs. And we name the segment. So this guy here is called the A segment. And we just go around, just rotate around the right, A, B, C, D, E, F. And the center segment we call the G segment.
I don't know this A segment.
It's just, you just know. I mean, you just learn it.
Right. So if we were just looking at that, or looking at another one, what would make us identify just that end as A?
Well, what we normally, first of all, you would have the pin out if you looked at it. Normally, and this one's not wired up, is normally we have a decimal point on one side.
Okay.
This is not considered to be part of the 7 segments. And usually when they make them, let's see if I've got them open. I might have to do this. These things come in all different sizes. But this is typical of the way they look. And so what you do, you see the 2 decimal points here? See them? Now they might not even, what they do is the space they put on this is the standard for all the 7 segment displays they make, whether common anode or common cathode. So these decimal points might not even be wired up, but they're the cover that they use. Does that make sense? So if the decimal points, it means so this will be the A segment, this will be B, C, D, E, F, and then G would be the center. And then you can buy them with left-hand decimal points, you can buy them with right-hand decimal points, or you don't have to buy them with any decimal. The decimal points are not considered to be part of the 7 segment display. You still have, and decoders don't support the decimal points. You have to decide when the decimal point turns on or turns off. Even your calculators use this same feature. They use a 7 segment display, but instead of using LEDs, they're using LCDs, liquid crystal display, and they have to be backlit. So that means we've got a decoder that drives common anode, and we got a decoder that drives common cathodes. The main decoder that drives common anodes is a 7447, and the main decoder that drives common cathodes is a 7448. So here's a 7447. The pin out. Here they're showing us the actual segments here. So this would be my inputs, A, B, C, D. Now why they did it that way, I don't know. Normally when you see A, B, C like that, the A is the least significant bit and the D would be the most significant. So if I was going to put a 3 on, a 5 on here, then this one would be low, right? I have to write this down. So 5 would be this. So high active input, so it means we don't have to invert the inputs. So it'd be a 5. But down here, this would be a 1. This would be a 0, right? You understand? This would be a 0, and that would be a 1. That would be a 5. Now what's going to come on, which outputs are going to go low, is what's ever required to display a 5, which is going to be what? A, B, C, D, E, F, and G. So this thing will output lows to display a 5 for us. Now the problem is that these are open collector outputs. What does open collector mean? So a totem pole output, we have a NPN up here. We have a resistor right there. Then we have a diode right here. Then we have a resistor right here. I'm sorry, then we have another transistor. And we call this the sinking transistor. The sinking transistor provides the low. We call this a sourcing transistor. It provides the high. These two guys are never on at the same time. But what would happen if we came up here and got rid of this guy right here? And we bring this collector out. That's my output. It means these guys can't source. The only thing they can do is sink. They cannot output a high. That's open collector. But what I can do on this guy is I can take the output of this, right? You understand? Now I can run it through that resistor. I can run it through an LED, and then I can run this back to plus 5 volts. So when the G output goes low, this transistor turns on, provides the what? Provides the ground. That forward biases my LED. My LED comes on. When this output, it don't go high, it cuts off. We no longer have our ground. Now the LED turns off. So I don't have to provide the high, but we hook that. We hook the 5 volts up to the what? Up to the LED itself. So this guy don't need to provide a high. All he's got to do is provide the what? The ground. So these guys have open collector outputs. One of our instructors was teaching the class, and they wired up. And she said, this 7442 is not doing what it's supposed to be. She had a 7447 for one thing. And she wasn't getting true highs out of it because she was using it as a 7442, right? You understand? She wasn't getting true highs out, and it was doing crazy things. And I said, well, you're using a 7447. That's a 7-segment display, common anode. So the anodes, we call it a common anode. Why? Because all these, so a 7447 outputs, oops, got to have a what? A resistor right there. Because what would happen if I didn't have the resistor? When that transistor provided that ground, it's going to be over 5 volts, right? Plus, we can use greater than 5. So we have a term called, we have these weird guys down here called ripple blanking device. We have a lamp test. So if the lamp test went low, what would you think would happen? All the outputs would go low, and my 7-segment display would display an 8. So you'll see some places that have a little thing where you can press it. So if your display is doing something weird, you want to see if the 7447 is actually outputting lows, if one of the outputs is bad. Ripple blanking was a technique we came up with a long time ago where we could share things. So the problem is our eyes can only update so fast, right? You understand that? And if we do it at a certain speed, then it appears like things are in motion. So y'all know movies and TV is just pictures. We call them frames. And what do they do with those frames, those pictures? They send them at a what? At a speed that our eyes just do what? Just blends them together and makes things look like they're in motion. These lights right here are flashing. They're literally turning off 120 times a second. These guys are turning off 120 times a second. But our eyes see them what? We see them on all the time. Why? Yeah, they update quicker than our eyes can update, right? So they said, why do I need to run a 7447 for every LED? Why can't I turn this guy on or turn it off, turn it on? We call that ripple blanking, by the way, where they can blank this display, turn on another one, right? That makes sense? Blank this and then turn on it. If you ever like put a motion picture on like on your DVD player or something that got clocked on it, you ever notice it looks like it's flashing? Why? Because your camera, your movie projector's taking pictures, right? And your display is blanking all the time, and your camera can pick that up if they're not synchronous. You ever notice that? You ever notice when you take a picture of the fluorescent lights, it don't flash, that it turns out yellow? I never noticed that before. Has a yellow tint to it. Because your camera actually sees the true lights there, right? It don't average it. And you see people that they'll have a shirt one color and you go out in the sunlight and it looks like it's a different color. Because why? Because this light up here is not true. It's a flashing light. We used to use it to set the speed on a disk drive. We could flash things at something. I don't know if you ever anybody had an old car you had to set the timing on? It's all done electronically. So what they can do is they can use the ripple blanking to turn this guy off and turn the next guy on to it, right? You understand? And turn it off and turn it, and then the displays are actually, normally the displays are actually turning off and on, which is pretty neat, but they share the same data path. So this is the inside, a lot to it, ain't it? This is the truth table. Now what would happen, so a seven segment display will only display characters from numbers from 0 to 9. What happens if you put a 10 on the input? So here's a 10. So if you put a 10 on it, it would turn on segment A. It would turn on segment B. It would turn on segment C. And it would turn on segment F. What numbers? Huh? No, it's a nothing. So this thing decodes it because of the layout of the gate. It'll decode things above 9, but it's going to be weird. I don't know if they got a chart. No, sometimes they give a chart that shows you the weird letters that will display. A 15 would turn them all. A 15 would turn them all what? On, yeah. A 14 would turn on A. Yeah, so it'd display an 8, but it's not a true 8, it's a 15. It'd turn on B. It'd turn on C. So if you happen to put a 14 on there, it would display that thing right there. Well, it's not a nothing. Oh, wow, yeah, it is a 7, sorry. So it should be doing the same thing.
So the low displays and the high is turned off.
Yes. Because this is a common anode driver. So a common anode driver means a common anode display. All the anodes are connected together, right? So if these guys are connected together, and then I run this up to plus 5 volts, then what's it looking to turn them on? It's looking for a low to turn them on. So this guy, a 7447, outputs a low because it's a common anode driver. Does that make sense? A 7448 is going to output a high because it's a common cathode driver. Of course, what I'm going to do on this one is I'm going to put a watt right here. Now, you see sometimes they'll put one resistor right here, but the problem with using one resistor is the more segments you turn on, the dimmer it gets, right? That makes sense? So most of the time we'll put a resistor on both of them. And if that's the A LED, then what I would do is I would hook it up to the A output on the 7447. Now that's got a pin. There's no such thing as a pin, right? So what we'd have to do is we'd have to look at the pin out So the A segment is where? Yeah, the A segment would be right there. That would be output, but it would be pin what? 13. That makes sense? Huh? So this guy right here, I'd almost bet if we got into this guy right here, it's going to have, it's blanking too, that guy, by the way. But I guarantee you, if we got into this guy right here, we'd either find a 7447 or we'd find a 7448, depending on what type of 7-segment display. So that's a 7-segment display right there. And here you can actually see the break in the lines. Where each segment. So see, that would be, see the segment. This is a 7-segment display, so you're going to run into these all over. So your digital multimeter uses a 7-segment display. Now it's not a, could a 7447 run that? No. LCDs are really weird. We'd have to talk about those, but it's still a 7-segment display, right? You understand? So your multimeters use it. Most watches don't use it anymore because they can display a lot of different information. But you know, we still run into these 7-segment displays all over. A lot of digital clocks still use 7-segment displays. If you got one of those. Multiplexers. What's multiplexing? Multiplex. One, yeah. So what we do, what's media? Yeah, what information travels through it. Okay, so sometimes we have to multiply. We have no option. So everybody's got a cell phone in here, and what's our media for our cell phone? Air. How many people's got cell phones, right? So we got a bunch of, so what's multiplexing? Well, all your broadcast radio stations are flying through the air, right? All your broadcast TV stations are flying through the air. How many cables do you have running in the back of your TV or your box? One. How many channels do you have riding on that thing? A bunch. Plus your network, right? So usually your internet comes through that cable too, right? So multiplexing is when we let multiple signals share the same medium. That makes sense. So multiplexing, multiple signals share the same media. We have two types. We have what we call time domain multiplexing. One signal on the media at a time. Each signal uses the entire bandwidth of the media. What's bandwidth? So you hear that term all the time, but you don't know what it means, right? We had a guy worked up at Forbes up there, the distribution center, and he worked at the desk, and he knew all these terms. But he had no idea what they meant. So he could talk the language, but he could talk to these people, but he didn't know what they meant. So he came through the associate's degree program here, and he said, "Oh, now I understand. Because he learned what all these terms mean. So you hear multiplexing all the time, but you hear bandwidth all the time, but you have no idea what it means. So anybody can guess what it means. So just about every media has a range of frequencies that it can reliably pass. So the range of frequencies that it can reliably pass. So I can't send 0 hertz through the air. You just can't do it. So we start sending a frequency through the air. And then the higher we get, it gets up, and then eventually it's going to start dropping down. So the range of frequencies a media can reliably pass is truly the bandwidth. It became to me the range of frequencies that I assigned to. So when we talk about broadband, that means your cable company says, okay, I'm going to give you 10 megabit, I'm going to give you 10 they use megahertz. I'm going to give 10 megahertz worth of bandwidth, right? You understand that? So bandwidth could also be the range of frequencies they do what? They assign you. So we got two ways. So what's nice about time domain multiplexing is that, by George, when you have the media, you got the entire bandwidth of the media. Frequency domain multiplexing, more than one signal shares the what? The bandwidth of the media. Each signal rides on a carrier, which we call modulation. Are we okay? This makes sense. Yes or no? So this is technically baseband is time domain multiplexing. Broadband is what we call frequency domain multiplexing, and that's what y'all hear all the time is broadband. So this is what baseband does. When I get access to the media, if that media has got 100 megahertz bandwidth available, then I get what? I get 100 megabits. Broadband, if you've got 100 megabits available and you might be assigned 10 megahertz. But the problem is, how many people are on the network here? Where's my mouse at? Baseband, there's only one person on the network. Broadband, I had what? In my example, I had how many? 10. So which one's better? Depends. They both have. So right now, if nobody in this college is on this network, we got a 100 megabit network, then I get 100 megabits. Right? You understand? If there's two people on it, then I've got access to it. But when I've got access to it, I get 100 megabits. Then the other person gets access to it. They get 100 megabits. And then another person gets access to it. They get 100 megabits. So the less people that's on there, the better the bandwidth I have on baseband. Broadband, you're almost guaranteed time, right? You understand? Because you're sharing that bandwidth with several different people. But Windows 10 comes with I don't know what they call it, but it's free. It lets you look at the bandwidth that you're giving. So don't take for granted. If you got Windows 10, you need to get that so you can make sure your cable company or whoever's giving you your bandwidth is giving you the bandwidth they want. But notice most of them don't say 200 megabits. They say up to 200 megabits. Right? So we still have a problem with broadband. So if I've got 10 slots in my bandwidth, and the 11th person wants to get on there, they still have to do what? They still have to wait. So even with broadband, you have a better chance of getting access when you got high rates, right? You understand? Than you do on baseband. So baseband is time domain multiplexing. Each device uses the entire bandwidth of the network when transmitting data. Your telephone system is baseband. Depends on where you're at. Ethernet is baseband. USB uses baseband, and Wi-Fi uses baseband. Broadband, also frequency domain multiplexing. Several devices share the bandwidth of the network when transmitting data, television, radio, cable, and then cable uses broadband, and then of course something called T-carrier. So Ethernet uses something called carrier sense multiple access with collision detection. I don't know if y'all remember, if you ever watched Beverly Hillbillies, Granny always wanted what they call a party line. When I was a kid, that's what we had. So party line means you had multiple families phones sharing the bandwidth. So what you would do is before you made a call, you'd pick up the receiver and what? See if there's anybody who's on there. If somebody was on there, you'd hang it up. And you'd wait a little while and come back what? Pick it up. See if it's on there. Now, if you got up there and nobody was on there, then what would you do? You'd dial the number of who you wanted to call. So everybody that was on your party line would constantly be doing what? Checking to see it. If nobody wanted it though, sooner or later you'd say, get off the line, I need to make it work. So that's what carrier sense does. So Ethernet, what it does, the network card or your Wi-Fi card listens to see if there's anybody on the network. If there's nobody on the network, then what it will do, it'll take the network. But what it does is it don't grab it. It sends what we call a packet. So all your data is split up in these packets. It sends one packet, and then it comes off, then it releases the network. If nobody's else, then it listens again. If nobody's on there, it'll send another packet, and send another packet, and send another packet, right? Does that make sense? But if you come off and somebody's out there waiting, then they'll grab it, and then you gotta fall in line and wait your turn. So what we're saying, the fewer people you have on time domain multiplexing or baseband, the more bandwidth you get. That makes sense? Of course, sometimes we have collisions. So I say nobody's out there. Somebody else has been out there. I say nobody's out there. I come off, try to put my packet on there, but somebody else is on there, right? And I hit it, and then I collide with their packet. So as soon as we get a collision, both the network cards do what? They come off, and then they try to get back on. So they have what they call random number generators. So you come off different times, and you come back on. So that's the way baseband works. Broadband basically works sort of like that, but nice about broadband is you get less bandwidth, but you're almost guaranteed a connection. So our digital multiplexers, these are all time domain multiplexers. So that's basically what the multiplexer does. It acts like a switch. I have multiple data inputs, and what does it do? It switches between the inputs. And then that's what goes out the data lines. What we do on most multiplexers is we have the ability to select which input we want to go through. So if I come up here and put zeros on here, then this switch is going to move up to 0, and 0 is passed through the output. If I come up here and put a 2 on here, then it switches down to what? It switches down to 2, and then 2 goes out. But we have the ability to select which inputs if we just wanted to rotate through them, then we'd just put like a counter or something on there and let it just rotate through. So these are digital multiplexers, and this would be what we call time domain multiplexing. So time domain multiplexing means as long as I hold that 0 down there, then input 0 is going to be passed through forever. Right? Does that make sense? Yes or no? So what's the advantage of multiplexing? Media, right? You understand? So it allows you to have 200 and some channels on there, right? Coming in on one cable. It allows all of us to be talking on our cell phone at the same time, right? Because we're multiplexing. Now, all those are broadband, right, or frequency domain multiplexing. What we do on baseband is we save conductors. So up here we got 4 wires. On Ethernet uses 4 wires. One of them's transmit, one of them's receive. And how many computers can be on that thing at one time? 1. But if I was to have 15 people on there, then I'd be running 15 different wires, right, for every computer. Make sense? If I wanted 300 people on there, I'd have to have 300 wires running to all of those computers, right? And then I'd have a problem getting to every computer on the network. So Ethernet uses baseband, which is time domain multiplexing. So is my computer using the network right now? No. So the only time you're actually using the network is when you're downloading something, when you're uploading something, when you're checking your email, right? You understand that? So time domain works out well there, right? But when I'm trying to send 15 channels or 200 channels at the same time domain multiplexing just wouldn't work out. So we take the bandwidth of the media, then we divide it into little different cells, right? You understand that? And then we share that. So I think the multiplexer we look at is 74139, which is a 4-line. I'm sorry, if we're going to multiplex it, we need to do what? Sooner or later, we need to do what? Demultiplex. So what would a demultiplexer do? It would take multiplexer lines, right, and route it to individual output. So what I would do is I would send this over to a demultiplexer. Demultiplexer would be set up basically the same way. So let's say this is a 0. This would be 1, 2, 3. What we would do is we'd send the switch lines over here with it. Now this is not, and this would be controlling the position of the switch. So what we do is if I'm put zeros over here, this would select 0. This would come out and go back. This is going to send it back out 0, right? Understand? Now this is not very beneficial but we're saving one wire. So I'm sending 4 bits of information. It requires 3 wires. So I've saved a wire. I could come over here and add another bit, right? You understand? I'm sorry. If I add another one over here, then I can multiplex 7 wires. So an 8-bit multiplexer would have 3 status lines, right? I'd be sending a byte of information over 4 wires. So what I've done is I've saved 4 wires. If I add one more select bit, that means I'm using 16, I'm multiplexing 16 signals, right? You understand that? 16 signals on 5 wires. So on time domain multiplexing, the advantage of these multiplexers is you can send information, but on fewer wires. But what that's going to do is going to limit your speeds, right? You understand that? Because if I'm constantly switching between them to save this time, then what's going to happen is you can't get the speed. So the more you put on that single wire, the less bandwidth each one of them's going to get. Right? They're going to get the same bandwidth when they're on there. But if you got 100 megabits here, right? You understand, for 1 second, then you have 0 bandwidth for 1 second, and then 100 megabits for 1 second. Then you're understand what I'm trying to get across. Yes or no? So time domain multiplexing, when I've got access to this wire right here, then I get the entire bandwidth. But the problem is, sooner or later, you're going to have to switch it over to somebody else, right? You understand? So if I left this on 0 all the time, then I would run a piece of wire. I wouldn't be using the multiplexer. So what happens is, as soon as this switches over to 1, then 0 has the information coming in on 0 is not being passed anymore, right? Does that make sense? So the problem is, if I rotate through this, then that means each one of them is going to only have what? They get a lot of bandwidth, but then they got to come off for a while, for a certain amount of time. So multiplexing is great, but what we do is we sacrifice speed, right? No matter which form you're using, whether you're using frequency domain or time domain multiplexing, you're sacrificing speed. But the problem is that sometimes we have to multiplex, because how many airs do we have? 1. And we're sending all type of information through this air. But each one of them's modulated, right? So what we do is we put them on what we call a carrier. So what we would do is I might have a carrier, and the carriers are usually AC. And then I can do one of 2 things. I can take that carrier and I can change the amplitude. So if I send in a 1, it might be a high amplitude. If I send in a 0, it might be a low amplitude. Now on radio, we call this AM. Y'all know what AM stands for?
Oh,
Amplitude modulation. So the sound, the carrier's running at a constant frequency, and what we're doing is the sound is modulating the what? The amplitude. Now the problem with that is that electromagnetic interference generates voltage. So AM is very noisy. But what we're doing is we would take my voice and we would cause it to modulate the amplitude. So what was FM? Frequency domain multiplication. So what we would do is while we send the information, we might have it doing this, and then it might do this, and then it might do that, but the amplitude stays the same, but what we do is we change the frequency. It's real hard for noise to change the frequency. Electrical noise can change the amplitude, but it's hard to change the frequency.
On the radio, why is it different when you change? Like when you go to frequency, you got channels, you got like 95.
Well, the problem is the modulation frequencies. So modulation for AM is down in the kilohertz, and that's the carrier frequency. So it was the first way they decided to send sound and stuff over the network. So they was having problems with electronic devices responding to extreme high frequencies. So that means all your AM dials are kilohertz. And what we do, guys, is we have what we call tuned circuits where we can strip off the carrier, and then we actually end up with the noise that we hit. If you're in AC, they'll talk a little bit about tuned circuits, where we can set up filters, and what a filter will do is it'll strip off the carrier and let the information come through. So we have the two that we know in FM is up in the megahertz, and that's what you're doing, guys, is you're setting up a tuned circuit. Have you ever looked at your dial and it says 93.7 megahertz? Well, that's the frequency of the carrier. And what you do when you tune your radio is you're setting up a tuned circuit that only lets that frequency come through. And then they strip off the carrier, and then you hear your sound. But it blocks everybody else. Y'all understand it? It blocks all the other radio stations because they're riding on a different frequency carrier.
Because I know, I usually, like, I remember doing something like this. Like, now, you can hear like two stations on one channel.
And sometimes you can, AM was real bad, especially in bad weather, because AM carries a long way. You could actually hear, when it started raining and stuff like that, you might hear somebody up in Chicago, but they're assigned the same carrier frequency. It's just that they say, these guys are not going to be close enough to do what? But they interfere with each other. And sometimes you can hear that on FM too, where you can pick up two channels on nights where it carries really well. Ham radio operators call it, they say talking skip. So you get those clouds up in the air and it really bounces off. And they can talk a lot further in bad nights on it. What's that? It's satellite radio, but it's still on a carrier. You still have a carrier, right? You understand? Yeah, but a standard radio can't pick it up, right? You gotta have that capabilities on your radio because there's not a tuned circuit in there that picks up that carrier. And you pay for those, right? But you have but even inside that, you still have, there they send you what you want, right? Don't you select the type of music you want to listen to? Yeah. So modulation means, but eventually if we modulate it, we're going to have to demodulate it. So I need a device that modulates, and then I need a device that demodulates. So if we have one unit to do that, we call them modems. So what they do you have to have a modem to access the what? The cable, because you have to modulate it on a frequency to make it fly on the cable, and then when you get it back, you got to do what? You got to so that's what the modem is. It's a modulator demodulator. Places it on a carrier when you send it, right? It makes it compatible with the cable, and then when it comes in, it does what? demodulates it so you can do stuff. So y'all now know what a modem is. Well, multiplexing, guys, this allows things to do, but we only got so much bandwidth, right? You understand that? And of course, what they do, they assign, what the FCC does is assign frequency bands, right? Where we have low frequency, we have high frequency, we have ultra high frequency, we have radio frequencies, right? And then you'd have to be within those bands. Okay, so that's this chapter. I know y'all was supposed to do that, right? Multiplexing, 74154. I'm sorry, 74151. 74154 is a. So 74154 is a decoder. Yes. Always. These tests will always have a written part, and they'll always have a multiplication. 74154. Oh, by the way, if you ever look at the 74154, it's going to be called a decoder demultiplexer. So what they're doing, notice what they're doing. They're leaving the enable low. Then they're coming up here and they're selecting a 5. Can y'all see that? Yes or no? So every time the input goes low, every time the input goes high, then the output would go high because it would be disabled. Every time the input goes low, it would be enabled and output 5 would go low. So what we're doing, but if I came over here and did this, then output 4 would be switching with the input. So what we would do is this would be our signal. It's multiplex. These would be the lines coming over from my multiplexer. So this would be my multiplexer. And whatever's coming in on input, let's say input 3. Let's say it's doing something weird like this. Well, what I would do is if I'm selecting input 3, I would come over here and I would send this right here. That would allow this signal to go on the output. So when it went high, that would disable the chip and output 3 would go high. When it went low, that would enable the chip and output 3 would go low. So what we're doing is we're taking 3, we send all the wires, right? But how many wires are we using? We're using 5 wires, and I can multiplex 16 signals on 5 wires. So what did I do? I just saved what? I saved 11 wires. So you see multiplexing used a lot because it saves media, right? You understand that? It allows us. So parity. So what's parity?
Oh yeah, parity, parity. That's kind of one. Sending the right amount of period from one to the other.
So right off the bat, they knew that we needed to send information, right? But the problem is I want to make sure the information that I sent is the information that's being received. You never count zeros. You always count 1. So parity is based on the number of 1s. So this is why ASCII code, if you look at the original ASCII code, it's a 7-bit code. But we are using 8 bits. So why is the code a 7-bit code? Because what they did is they used the 8th bit for parity. So I would come over here, but your transmitter and receiver has to be set up to run the same parity. Now, we used to have to do this, guys. But now just about everything is what we call PNP. You know what that means? Not transistor. It's called plug and play. So what happens is the information that this thing needs is inside this thing right here. So as soon as I plug this thing in and it says, okay, there's somebody out there, it says, what do you need? This guy says, well, this is what I need, and it automatically configures that port to generate what it needs to generate to communicate with this thing. So the problem we have now is that we don't really know, right? You understand? But it's still there, right? Didn't I take you into the settings on the system, found the COM ports, and said that I would select even, odd, right? You understand that? Y'all remember that? So what happened is your receiver has to be set up the same. So if this guy right here is transmitting odd parity, then this guy is going to be set up to do what? Receive odd parity. So that means I'll make up an 8-bit code. We can look it up in the ASCII code chart. So that's 7 bits, right? You understand? And I'm set up for odd parity. So what would this guy do? Well, it's going to count the number of ones. 1, 2, 3, 4. Is that even or is that odd? Okay, so what it would do, it would come up here and take this last bit with the parity bit, and it would set it to a 1. You count the number of ones. It has nothing to do. It has nothing to do with which way you count, Melvin. I mean, the parity bit is always the most significant bit. I understand now. So the parity bit would always be the most significant bit, no matter what you're running. So the parity bit would be on a byte. It would be. Now IBM, when they first came out with their memory, the technology was not that great, and we were storing information in bytes. And each chip would only hold 1 bit. It'd hold a bunch of bits, but if you counted the memory, there would be 9 of them. Even though we were storing information in bits. What was that 9? What was that 9th bit used for? Parity. So originally when dynamic memory came out, it was very unreliable. It had problems all the time. So what they did is they put parity. Now memory now is so good, we don't use parity in the memory of the computer because it's so good. On a server, that server over has got something called ECC memory in it, which is error checking and correcting memory on that sucker. So that sucker can that memory not only knows if the information is bad, it comes up and can do what? Fix it. Yeah, but that's pretty expensive. We run that in servers where information is very, very critical. So the way you count the number of ones and the way the receiver counts them, we don't really know. All we know is just counts the number of ones. And it's going to set or clear the parity bit to make both of them match the number of ones, right? Does that make sense? Is that an even number of, is 0 an even number of odd number? Even, yeah, you're right. So it wouldn't set it. I mean, here it would set it if it was all 0. Right? You understand? So yeah, that's a good point. So 0 is considered an even number, right? 0, 2, 4, 6, 8, right? So you're right. If I was to come up and do this, which is a control code, by the way, then my generator would set the parity. Then this guy over here receives it, right? You understand?
That'll make that odd parity, right?
Yeah, because that's what we got up here. That's what we're doing right now. We're doing odd parity right now. Now, what would happen is if we look at the ASCII code chart, the first 2 columns are what we call control code. So we have what we call handshake. And we run into handshaking all the time between 2 devices. Handshake is what we use to determine if the receiver says the data is what? okay or not okay. And thank goodness for this handshake. We got two ways we can do handshake. We can do what we call software handshake, where the two devices sends codes between each other. Okay. Or we can do what we call hardware handshake, where the devices actually have signals to do that with. So if we got software handshake, ASCII is set up for software handshake. So here's the first two columns. Null, start of header, start of text, end of transmission, inquiry, acknowledge. These are the two guys right here. ACK and what? So this is what would happen. I'd send thing out with parity, and then I'd wait on the receiver to either send me back an acknowledge or what? A not acknowledge. If it send me back an acknowledge, I would send it to the next paragraph. If it send me back a not acknowledge, I would do what? I would resend the last character. And this is what TCP/IP, which is the internet protocol we use, uses software handshake. So every byte that comes over there does what? Is checked to see if what was sent is what was received. Now it uses a different method that we won't get into, that it's software handshake. Hardware handshake means I would literally have wires running that says acknowledge and not acknowledge, right? You understand that? So a software handshake is very, very popular. So how many hairs do we have? So when all these packets are flying through the air to your phone and to your computer and stuff like that, we need a method so we know that what's being received is what was being transmitted. And TCP is what they call a connection-oriented protocol, which means by George it uses software handshake. So what you do is you sacrifice bandwidth for this error stuff, right? You understand? But at least you're guaranteed when you download a file, you get the file that was downloaded. There's another one called UTP, which is non-connection. It's a lot faster, but the data you get is not what? It's not guaranteed, but it uses the same packet. It's the same transmission. It uses IP for protocols. Because TCP is a transmission control protocol, and that's where all the software and the packets and all that are. And y'all familiar with IP, right? Y'all not familiar with IP addresses? So that's the addressing scheme of the TCP/IP protocol. IP is the address and how you address a computer. TCP is how the packets are put together and what type of error correction is available. So TCP is what they call a connection-oriented protocol, which means it checks to make sure you got the connection before it sends data, and then it has error correcting information in it. So y'all learned a little about network. Luckily, I've been around while most of this came into play. We set up a network in our department before the college had a network. So we run our own server. So that's our domain server, that black box right there. And we're the only department in the college that they let do that because they know we do what? They know we do it right. Yeah. So that little old box right there, that's a 6 terabyte file server right there. That's our domain server up there. So when you log into met.stu welcome, you're logging in through that guy right there. We run our own network. If it's already odd, then the parity bit would be 0, right? If the number of ones are a 1, then not in the data, not the parity bit. So the receiver, what it does, it counts all the bits, including the parity bit. And then it throws the parity bit away, because that's not what I'm sending. When I send the letter A. So the letter A, no, I can't remember on the. So the letter A would be what? 41, right? You understand that? And depending on running even or odd, so 41, would that be even or odd? Would that be an even number of ones or an odd number? Huh? Yeah. Well, no, 41 in binary, right? But this is hex, right? So that'd be even or odd. 41. It's not if the number is even, it's the number of one. So 41 is an odd number. But we're not looking at if the number is even or if the number is odd. We're looking for either an odd number of ones or an even number of ones. So 41. That's even, right? Because there's what? 2 ones. So this gets people confused because they say it's an odd number, but parity has nothing to do with the number is even or whether the number is odd. It's counting the number of what? 1. So what would my parity bit be at if I was sending the letter A? So I'm sending the letter A from this receiver, from the transmitter to receiver. Okay, so I'm running what? Odd parity, so my parity bit would be a 1. Now, if I was using even parity, then what would happen if one was set for even parity and one was set for odd parity? Yeah, well, it would transmit, but the receiver would always say not acknowledged, not acknowledged, not acknowledged, not acknowledged, and it looked like the thing's not running, but your transmitter's constantly resending the what? The same data. So yeah, you need to make sure. So used to, you had these little switches. Some of your receivers, you had to read the documents because it would be set for what? Even or odd. So you had the ability to configure your port for even and odd. But the parallel port was hardware handshake, so we didn't have to worry about the parallel port because all the devices used hardware handshake. We had a port called a COM port, which is very similar to USB, but it was a lot slower. That sucker was software handshake. So what you had to do on that COM port is you had to make sure that you had the ability to do what? So I'm going to go to what? I'm going to go to all programs, go to accessories. I'm going to go to system tools. No, there's an easier way to do this, folks. Device manager. And right here, these COM ports. Port settings. Right here gives me the ability to do what? Set my parity. So right now, this guy is set up to generate and check what? Even parity. This was a bi-directional port, by the way. But what happens is we don't see this anymore. Why? Because of plug and play. Everything's plug and play. So this COM port was set up for me. So something in here thinks it's a COM port, even though I don't have the COM ports out here anymore. This is where we set the bit speed. So the fastest we could go on the COM ports was 128 kilobits per second. That's slow, right? So we'll leave this thing alone. And stop bits, I said it for odd parity. Or we could always make the parity a 1 for some reason. They call that a mark. Or we could always make the parity a 0, right? So we could turn it off or not use a parity bit. or we could set it to what? Even, or we could set it to odd. And right now we don't know it because it's done for us automatically. But if you ever, by the way, we don't have the old serial ports anymore. But why? We don't have the old parallel ports anymore, which was really, really neat. Because USB allows you to buy these things they call dongles, right? You understand? Where you can plug it into the USB port and it'll make it act like the old RS-232 ports. I'll have to show y'all one of those. You can get it for parallel. You can get the old IEEE 1284, which was the parallel port. Your computer don't need that anymore. If you need one, you can buy what? You could buy a converter. That'll take you from USB back to parallel. You can buy a converter that takes you from USB over to the old COM port. So that's why those ports are not on your computer anymore. But just about every desktop will have a WAD on. Will have a USB port, at least one USB port. So that answer your question?
Yeah.
Any more? So we're not going to have time to go to labs. Let me bring up the test review for y'all. Draw the output waveforms for ANDs, ORs, NANDs, NORs, exclusive ORs. So that'd be hard to do on multiple choice, right? Parity, even parity, odd parity, digital comparator, magnitude comparator, exclusive OR, exclusive NOR, synchronous, asynchronous. So we talked about that. Synchronous is when we send the information and we time it with a clock. Asynchronous is information that is not timed with a clock. Propagation delay. What's propagation delay? What's propagation delay? I know we talked about that. That wasn't even on the video. We talked about that in class. Propagate means to move through, right? Propagation delay would be the amount of time it takes the outputs to respond to the inputs. Every gate has a propagation delay. It cannot respond instantly, right? You understand that? You have a propagation delay. I think I told you about me locking the keys up in my car, right? Or I had my keys in my hand. They slipped out of my hand and I watched myself close the trunk. I watched those keys slide down through there, in through the slot, and I still did what? I still closed the trunk. Because I had a propagation delay between my brain thinking, processing that information, and sending it to the muscle of my car and saying what? So when they say you have fast reflexes, what are they saying? Well, they're saying you have a low propagation delay, right? It gets to your hands, to your muscles real fast. So everything has a propagation delay. We can't go from here to there in no time. So it takes time for these signals to propagate through these gates. Rule of thumb for standard TTL is 10 nanoseconds. But where do we need to find that at? We need to look it up in the data sheets, right? You understand? And high to low and low to high, sometimes it's not the same. On your S series gates, they'll be really close. We call them shotkeys. Rise time, fall times. Are you okay there? Totem pole outputs. Are we okay there? Fan out. Are we okay there now? Right. Duty cycle. What's a duty cycle? It's the percent of the period that the signal is high, right? You understand? Level triggered, edge triggered. We hadn't have time to get into that. I need to show you all that, so I'll make sure that's not on the test. Rising edge and falling edge, you're okay there, right? Sinking and sourcing, you're okay there. Absolute maximum ratings, you know what those are? Huh? On your data sheets. What are those? They don't guarantee operation. They just mean the sucker's not going to burn up on you. Right? Don't mean they're going to operate right. Then we have pull-up resistor. Is everybody okay there? Pull-down resistor. Do I have that on there? A buffer. Everybody okay there? What's a buffer? Just pass through. You get a propagation delay. We do buffers. I think the example we use to increase fan out. So you can bring the output of a gate, you can bring it to a buffer, and then it'll give you the fan out of the buffer, right? You understand that? So we use it for buffer. We use it for isolation, so they're used. We normally don't teach them because they're not a gate. They're not one of the 5 basic gates. The 5 basic gates do something, right? Decoder, everybody okay there? Decoders, encoders, multiplexers, demultiplexers, time domain, multiplexing, frequency domain, multiplexing. So we just got through with those, right? We're going to give you a data sheet on the 7400 to 70. Of course, we're going to give you all the books, right? 7400, 7403, 7405, 7406, 74138, 142, 42, 154, 147, 47, and an 85. You all know what those are, right? No, but you can look them up, right? Know the general legal voltage levels for a high and low when troubleshooting TTL gates. What do we use for rule of thumb? TTL 2.4 above, 2.4 and above for a legal high. 400 millivolts for a legal low. Don't be sorry. Increasing the speed for us, by the way. We're supposed to get our own access point here for Wi-Fi. You can see it if you go into A250. They've already done. ANDs and OR gates, diode gates. That was on the last test. We won't put edge detection circuits on here. I'll show you all that. Characteristics, exclusive OR, inclusive NOR. Be able to write Boolean expressions given the digital circuits. Be able to draw the digital circuits given the Boolean expression. That was on the other test, right? Boolean equations for ANDs and NORs. Standard TTL circuits, minimum, maximum, max. Of course, you'll be able to get your what? Data sheets on that. So let's review for the test. There's 2 things I will take off right now. We didn't get to it. Is edge detectors. Which are really, really cool. And we'll wire one of those up and let y'all do that. So let's review. Like I said, I'll go ahead and I'll just mark those through because I don't want to take it off for another test. So we're behind a little bit in the class, but not too bad. So what's the plan? We'll come in and we'll do a lab, the first part of the class, right? And we'll take the test, the second part, not part of the class, toward the end of the class. Okay, any questions? All right, guys.